Hi everyone, I'm Anish and welcome to PrepFusion. So today we will be starting a new topic basically, that is the concept of controllability. So what is controllability in state space and why is it so important to us? Okay. So before that, right, I will go into the previous lecture notes and I will try to revise few things. So let me go to the previous notes. So yeah, let me start from the where did we start from the previous note? So I told you like few transformation decompositions and two of them we already did, right, the CCF and OCF. Now we will do the parallel and cascade like that we did in the previous lecture. So in parallel mainly two forms are there. One is diagonal canonical form and Jordan canonical form. By canonical, what do you mean? It is a minimal form. We need to choose the minimal number of state variables, okay, so that it can define my system fully. Okay, Jordan is just the difference is the eigenvectors are dependent. That means we have repeated eigenvectors. Okay, like if eigenvectors are vectors are dependent, then for sure I will have repeated eigenvalues. But if my eigenvalues are repeated, it doesn't mean that I will have surely dependent eigenvectors. Okay, just keep those in mind. But yeah, if my eigenvectors are repeated, then we will convert this into Jordan form, and if my eigenvectors are independent, then we will convert this into canonical like diagonal canonical form, which is also like where the eigenvalues are distinct, right? So yeah, that is basically what we did. So we had a parallel transformation. I took an example and did few things. Okay, we do the transformation. So all this I think we did fine. So these two are contained in parallel. That is fine, right? That is right. But then we wrote the state equation. But here, right here, what was the confusion? Like there may have been few confusion that I have repeated eigenvalues this time. Okay, and if like this is repeated, right, the poles are the eigenvalues of the system itself, that we already established, right? So if we have repeated eigenvalues, then what will happen? Then you might think that I will need three state variables, right? As this is order 3, I need three state variables. But this, right, this s plus 2 is already like stored. I will just need to reuse it again. Okay, so that's why I use three integrators here. As you can see, I use three integrators here. But for this one, right, like you would have asked, like I could have connected another integrator over here, right? Solve for this differently, right? Like where is the transfer function? Like as you can see, right, these are in addition. So I could have solved this differently, then this differently. But what is the problem? The order is 3. So what will be the minimum number of state variables? Tell me, what will be the minimum number of state variables? It is 3, right? It is 3. So I have to use only 3 integrators. So that is the main thing you have to keep in mind. So like here, right, I should write this here. Like if order is 3, where should I write? Yeah, poles are 3, right? Poles are 3. So number of integrators should also be 3. Minimum number of integrators. Obviously I can use more number of integrators, but minimum, the canonical form, for using the canonical form, the number of integrators should be 3. Okay, it should be 3 only. So if it is 3 only, right, then that's why I didn't calculate it separately. This one, right, this one, I just used this one only. Okay, that's why I just used another integrator with this one and I got to this form, right, to get to my minimal form. Okay, so that's why I didn't connect this here and used another integrator s minus to then connect this back to back. Okay, that was the reason. Okay, so yeah, there may have been a bit of doubt. So you check order is 3. Okay, hence the number of integrators will be 3. Okay, that is the main thing that I wanted to like convey like in this revision, like homework. I hope you did. Okay, if you didn't, you're like betraying yourself. Okay, so yeah, then we wrote a state equation, that is easy only. Okay, and cascade decomposition is not an important, it's very easy, you can do it. Okay, just convert this into CCF form or OCF form individually and then just connect them back to back, whatever you want to do. Okay, so yeah, and also one more thing, right, if you are in a doubt, okay, if you, anytime you are in a doubt that I have an integrator over here, okay, and I have the state variable, just before that you put another integrator. If you have doubt or confusion, you put a one gain over there, then you put the 2 indicators. Okay, then you put the 2 indicators, like what that helps is not get your answer wrong. Okay, you will never get your answer wrong. So one tip that I want to tell is basically always put a gain of 1 over here and then put the 2 indicators. If you are confused, like while writing the state equation, right, sometimes I get confused that I have like x2 dot here also and x1 in the same node. So how will I write it? So I'm not understanding that x1 is incoming to this x2 dot. Okay, for that reason. Okay, so yeah, that was basically it for the like this previous lecture. Now we'll move on to the next lecture. Okay, so now right, let's learn about what do controllability mean. So for knowing about what do you mean by controllability, what we'll do is basically take the help of an example. So here is example. Okay, this is a basic transient example, and this I think already like Himanshu has like taught you already all these things. So I have two circuits. We have to find the equation for Vc of t, that is the capacitor voltage for the following circuits, right? So in one case the Vi input voltage is 0 volts and the initial voltage is 0.5 volts. Okay, and in the other case the input voltage is a unit step, and the capacitor voltage is again like initial capacitor voltage is 0.5 volts. So in both of the cases the capacitor has some initial voltage of 0.5 volts, but in the first case the input voltage is 0 and second case the input voltage is 1. Now what I want you to do is you write in pen and paper the expressions for Vc of t in time domain, okay, with intuition as Himanshu has taught you. Okay, this is you have to do this now, then I will solve this. Okay, so yeah, I've already like drawn the case 1 and case 2. So tell me what will happen in the first case. As my input is 0, will my output also be always 0? No, right? So why? Because the capacitor has some voltage, right? It will decay as this is source free network, it will decay to 0, but at start it will have some voltage, that is 0.5 volts, and this is 1 farad and this is 1 ohm. So what will my equation? My equation will be 0.5 e raised to power minus t upon tau. Tau is 1 only. What is tau? Tau is R times C, right? So tau is 1 only. Okay, so this is 0.5 e raised to power minus t upon tau. Now right, now tell me what happens if we have an input, right? If we have an input, then what happens? This is plus minus 1 volt. Okay, this is 1 ohm, this is 1 farad. Okay, and yeah, like what is the, like I have initial voltage, right, 0.5 volts, and this is 1 volts. So what you will say? You will say, yeah, this is 1 volt source, so my transient equation will be 1 minus e raised to power minus t upon tau, which is 1 only. This is transient equation, but you're wrong. Why? Because I have an initial voltage also, so I have to take care of that. For that, how I used to write it, so I think Himanshu has taught it. If you like, obviously he has taught it. So what procedure I follow is I write like this one, right? So Vc of t will be equals to simply Vc of infinite 0 plus, okay, plus Vc of infinity minus Vc of 0 plus e raised to power minus t upon tau, right? So this is like my equation. Okay, sorry, wait some now, again I made some mistake. Yeah, sorry, like that's why I was getting confused. It is not that, it is Vc of t equals to Vc of infinity plus Vc of 0 plus, okay, let me write this in next page actually, that's why it's getting congested. Zero plus minus Vc of infinity e raised to power minus t upon tau. Tau is 1 only, right? So what is my Vc of infinity? Vc of infinity is basically 1, right? Because steady state this current is 0, so drop across this is 0, so this whole Vi comes across this capacitor. So this is 1 volt. Now what is the Vc of 0? Vc of 0 is 0.5, right? 0.5 volts. Okay, and this is 1 e raised to power minus t upon tau, and this is like 1 minus 0.5 e raised to power minus t, right? E raised to power minus t. Okay, so yeah, this is my basically Vc of t. This is my Vc of t. Okay, so yeah, now right, now tell me some is the difference. So this was the equation I was getting when there was no input, right? Input was 0, and this is the equation when there is some input, and Vc of t is changing. And what is VC of t in this circuit? So think like this in state space form, right? State space chapter. So think like, what is my VC of t? My VC of t is the state variable, right? VC of t is the state variable. So as I can see that when this input is not there, state variable is coming like this. But if I put the input, okay, I can get some value of state variable according to my desired, right? Desired nature. So if I change this input, then I will get the desired state variable value, okay, desired state of the system. Basically, what does this mean? This means the state, right? The value of the state variable means the state of the system. So I can get to the desired state what I want by providing an input, right? By providing input. So yeah, that is what basically controllability is. So like the future state of the system, if it can be defined by the input, okay, input, then the system is said to be fully controllable. Okay, here like I can define the future state, whatever, like here I put a unit step. If I had put a different like amplitude, then I would have gotten any desired, like let's say I want like 0.75 at t equals to 1 second. So I would have got that by putting my like desired input, and I will get my desired output. So I am controlling the future state of the system with the help of my present input, So if that is possible, right, if that is possible, then the system is said to be fully controllable, else we won't be able to control it. Okay, also like it also defines, like it does also mean, controllability also means how we are defining the system, right? How we're writing the equations and matrix. Okay, so yeah, we'll slowly learn all those, okay, understand and clear the concepts. But that is the main thing. That, let me write here that if we can control future state of the system with the help of input, then the system is said to be controllable. Then the system is said to be controllable. Okay, so like here, right, you might ask, here also I can get any value. No, here this is the initial value of the state. I can't change the initial value of the state, and the state future value of state is only depending on this initial value, right? So I am not able to do anything with it. Okay, not able to do anything with it. But here I am able to do, because this one term is also coming, right? One term is also coming. So I can control it. I can control it with my help. Okay, so like if the system we cannot control the system, future state of the system with the current input, right? With our current input, then what do you say? The system is uncontrollable. So let me copy this, okay, and again paste this here, right? Can't control with the help of then the system is said to be uncontrollable, not controllable, uncontrollable, right? Okay, so it's said to be uncontrollable. So yeah, that is basically it for the controllability and uncontrollability. But one more thing you have to keep in mind here is this is also depending on the state variable, initial value itself also, because due to this initial value we are getting some, like due to this initial value also we are getting some output. So yeah, it is depending on both input and state variable. Okay, but for controllability, what we will do is basically make our initial values to 0. Okay, so we can fully control the state variable with the help of input, right? Yeah, that is what basically we do generally. So here also I have written the key point, basically that future state of the system will depend on the eigenvalues of the system. What do you mean by eigenvalues of the system? Eigenvalues are the poles of the system, right? So like basically future state, right? Future state, if you see, what is the eigenvalue? It is a pole, right? So the pole will define the time constant here, and that is what will define the future state, right? Future state is defined by the time constant here. Also there is also initial like amplitude also, but it is also defined by the time constant. That is what basically this key point means. I hope you understand. Eigenvalue means pole, and pole is what for a first order system, it is 1 upon s tau. Pole is the negative of the magnitude of the time constant, right? So yeah, so this basically means that one. Now what I will do is, like this future state, right? How does it depend on eigenvalues, that I will explain. Okay, so I told you in brief. Okay, now I will take few cases. Like in one cases I will take all the eigenvalues as negative, the next case I will take all the eigenvalues as positive. Now you say, like you will see how does it how the future value of the state depend on the eigenvalues, right? That we will understand like in taking from one example. Okay, but in brief I also explained. But what does the eigenvalue means? Okay, what does the eigenvalue means? It means basically the poles of the system. Okay, it means basically the poles of the system. So yeah, let me take one example. Okay, if I take one example, right, a is equal to -1 0 0 -2. Okay, so if a is equal to -1 0 0 -2, and my b is equals to 1 -1. Okay, and my c equals to 1 1. So can you find the eigenvalues? So like here, right, not eigenvalues, can you find the poles and find the response of the system? So I will plot the response, and from there we will understand. So here, right, so our eigenvalue is negative here. What are my eigenvalues? Okay, what is the sum of my eigenvalues? It is the trace of the matrix, right? And what is the product of my eigenvalues? It is the determinant of the matrix. So this is 2 and the sum is basically -3, right? So yeah, my eigenvalues are -1 and -2. All of them are negative. My poles will be at -1 and -2. We'll solve this, and then also you will understand, right? So again, what is the formula of my transfer function? So transfer function, right? I have to first find the transfer function. So my transfer function is it si minus a inverse only. So I hope you remember, right? I hope you didn't forget there was one c also and b here also. Okay, and there was one d also, but in most of the cases, right, it is 0. That's why we ignored it. So like what is my c, right? So what is my c? C is 1 comma 1. Okay, now si minus a inverse, again I will do that trick, a b c d. Okay, and what is my b? B is 1 minus 1. So this becomes basically, right, this becomes like a times c. So this becomes a plus c, and like what will be this order? Order is 1 cross 2, and this is 2 cross 2, right? Always do that. Okay, then my final order will be 1 cross 2 only, right? So this is a plus c. Okay, and this is b plus d. So this is b plus d only. Okay, b plus d only. And what is this? This is 1 minus 1. Okay, 1 minus 1. So this is a plus c times minus times b plus d. So this becomes a plus c minus b plus d, right? This is my final expression. Now I have to find a b c d. So what are my a b c d? So basically, right, I don't get any minimization, but that's fine. Like my a b c d, right, this is my a b c d. A b c d is si minus a inverse, right? Simply it is s, and it was s minus minus 1, so it will be plus 1. This is 0, this is 0, this is s plus 2. Okay, and so this is the whole inverse, right? So this is the inverse. So what does this become? So this becomes, right, we swap the main diagonal elements and negate the sign, also divide by the determinant, right? So what is the determinant this time? Determinant is 1 by s plus 2 into s plus 1. Okay, so what does this become? Inverse. So abcd, right? So 50% of the terms are 0 only. So abcd becomes 1 by s plus 1. Okay, 0 1 by s plus 2. Okay, so yeah, this is what my abcd are. So like have to like add a and b and subtract this, right? So what I will get, basically my final answer will be 1 by s plus 1 minus 1 by s plus 2. Okay, so what will be my like final transfer function, it will be s plus 2 minus of s minus 1 divided by s plus 1 by s plus 2. Okay, so what will my transfer function become? So my transfer function, right, it will be 1 by s plus 1 into s plus 2. Okay, so this is what my transfer function will become. Okay, so this is my transfer function. Now what I wanted to find was the response, right, response in a system. So let's say this is a transfer function in a system. So I have a block, okay, which is a transfer function like this, and let's say I'm not giving it any feedback, right, I'm not giving it any feedback, I'm just seeing the open loop response. So this is my transfer function, and this is my input, which is e raised to power minus 3t into u of t, right? And what is this? The transfer function of this one, right, is the above one only. Okay, and then, right, what will the output I will get? The output y of s, what I will get is simply, let's say this is some u of s, okay, simply transfer function times the input, right, in Laplace domain, in normal, this is LTI system. So let me first say this is LTI system. Okay, LTI system. So for LTI system this is only valid. Obviously for LTI system only we have transfer function, right? So this is the LTI system, so it is transfer function times the input, right, u of s. Okay, so then, right, what is my u of s in Laplace? In time domain this is e raised to power minus 3t. So in Laplace what will it become? So I hope you are revising your formulas for Laplace transform. It is 1 by s plus 3. Okay, so what does it become? It becomes 1 by s plus 1 s plus 2 times s plus 3. Basically this 1 by s plus 3 term comes into multiplication, right, as this transfer function is this one. Okay, and 1 by s plus 3 is only getting multiplied with this one. Okay, so yeah, now, right, let me plot the response. So again, right, I have to plot the response in time domain, right, for us to understand is the system stable or not. Why? How will I understand? I'm giving a stable input, that is a bounded input. What do you mean by bounded? Basically t equals to infinity, right? T equals to infinity, the input is going to 0. It is not going unbounded, or it is not like it is settling, right? It is not like it is not settling, it is settling to some finite value 0. So my output also settled to some finite value. Okay, it shouldn't blow up to infinity, or it shouldn't like never settle, something like that. It should settle to some value. From that I will understand, as I'm giving a bounded input, I should also get a bounded output. From that I will understand my system is stable or unstable. So what should I do is do partial fraction, right? So if I do partial fraction, again I will do this directly in exam hall also. You have to do this directly. Okay, what I will do is put minus 1 over here. So this will be minus 1 2, so this is 1 and this is 2, so I get 1 by 2. So my y of s 1 by 2 by s plus 1. Okay, and what is my another? So my y of s is like now this one, right, this is minus 2 plus 2. So minus 2 here comes over here, so minus 2 plus 1, which is minus 1, and minus 2 is 1. So simply it becomes minus 1 by s plus 2, minus 1 by s plus 2. Okay, and what does like this become? I put minus 3, like s equals to minus 3. So I put minus 3, this becomes minus 1, and this becomes minus 2. So this becomes 1 by 2. Okay, so this becomes 1 by 2, and this is s plus 3, right? Now what I'll do, as this is broken down into partial fraction, I can simply do it in Laplace inverse, and I can simply find the Laplace inverse for each of them, as it follows principle of superposition, right? So this is simple only, right? This is simple only. What are the Laplace inverse of this, all this? So Laplace inverse of this one, so I get this y of t equals to 1 by 2 e raised to power minus t minus e raised to power minus 2t plus 1 by 2 e raised to power minus 3t, right? Okay, so what I am seeing at t equals to infinity, what is my y of t? Tell me, by seeing all this, at t equals to infinity, what is my y of t? My y of t is 0, right? My y of t is 0. Okay, so we are getting a bounded output. for a bounded input. Okay, so I should write here bounded output for a bounded input, right? So that is what we are getting. Now let's go for the case 2, right? Case 2 is what? When the eigenvalues are positive. What I'll do, I'll just simply negate the A matrix from the previous example. So if I take the previous example only, just make the signs opposite. So my A matrix, right? A matrix, what will it become? It will become 1 0 0 2. Okay, it will become 1 0 0 2. And what will be my B matrix? B matrix will be 1 minus 1, same only. And my C matrix, right? C matrix will be 1 1. Okay, so yeah, all of this will be my ABC matrix. Now let's do one thing again. Let's find the transfer function, right? Again I will do the same ABCD. So what will be my this SI minus A inverse into B? It will be A plus B minus C plus D. Okay, so now, right, this we know already, we got this from previous lecture, previous question example. So I will do the SI minus A inverse. So this is S minus 1. Okay, S minus 1 0, S minus 2 0. Okay, and this is basically my ABCD, right? The inverse of this one, inverse. So what will be this? So this, right, this basically is S minus 1 into S minus, so this will be swapped again. Okay, this will be 0 0, and I will divide by S minus 1. So what does this become? So this becomes S minus 1 0 0 1 by S minus 2. Okay, so like my ABCD are this, all this only. Okay, so like what will be my transfer function? T of S will be basically 1 by S minus 1 minus 1 by S minus 2. So this will be my transfer function, right? So it's like that only, right? This plus this minus this plus this one, right? AB plus A plus B minus C plus D, just like the previous question. So I hope like you got the previous question. So again, right, what will be my transfer function this time? So my transfer function will be S minus 2 minus S plus 1 divided by S minus 1 into S minus 2. So it becomes basically minus 1 by S minus 2, right? So this is what it becomes. So now, right, so we have been given an input. Okay, we have been given an input, and this is my transfer function. Okay, this is my transfer function, and again I will give the same input, same bounded input. Now I will see what output I am getting. Even though this is like a time response topic, still I will do this to like clear your concepts. So I am giving the same input, e raised to power minus 3t, and I am checking the output, and my transfer function is this one, right? So my transfer function is this one this time. Again, right, what will be my output? My output will be y of s equals to t of s times u of s. Okay, my output is transfer function into the input, right? So if that is my input, so now, right, what I will do here is, again, what is my u of s? U of s is 1 by s plus 3. So it is 1 by s plus 3. Same thing that we are doing, 1 by s plus 3. So what will be my y of s in Laplace? It is 1 by s plus 3, right? 1 by s plus 3, and this is 1 by s minus 1 into 1 by s minus 2. Okay, 1 by s minus 2, and also I have a negative sign also because this is a negative, right? That's why. Okay, so yeah, that was one thing to take care of. Now what I'll do, find my do partial decomposition of partial fraction of like this y of s. So I will put s equals to minus 3 first. So if I put s equals to minus 3, what do we get? This is minus 1 only in the above, this is minus 3, so this becomes minus 4 and this is becomes -5. Okay, and I have again s plus 3 here in the bottom, right? Now, right, if I put plus, now like, okay, -1 now, what I will do, I'll put this, okay, you can do it individually, but I will put this -1 at the outside, okay, so that I don't get confused anymore. So this will become 1 by, again I put s equals to 1, so this becomes 4 and this becomes -1, so this becomes 4 and this becomes -1, and yeah, this is s -1 plus, again I put s equals to 2 here to make it 0, right? I will calculate the coefficient of this, right? So this becomes 5 and this becomes 1, so this becomes 1/5, 1/5, right? So, and also like I forgetting the denominator s minus 2. Okay, so yeah, this is my transfer function basically. Okay, this 5 and s are very similar, so let me differentiate this. This is 5 and this is s. This is also s, right? So yeah, this is basically my transfer function, right? This is basically my transfer function. Okay, so again putting the negative sign inside, so this will be simply -1/20 divided by s plus 3. This will be plus 1/4 divided by s minus 1. This will be -1/5 divided by s minus 2. Okay, so basically this is what we get, right? So let me check. If I put s equals to 2 over here, this becomes 1 and this becomes 5. Yeah, so yeah, I get this 1/5 only, -1/5. Okay, so yeah, this is basically what we get. Okay, now let us do the Laplace inverse of this. So if I do the Laplace inverse of this, taking the Laplace inverse, okay, so what will be my Laplace inverse? So basically, right, basically if I do the Laplace inverse of this term, this is same only, we know it is s plus 3. So where is my pole? Pole is at negative left hand side of the s plane, right? j omega axis, it is on the left hand side. So what will be my exponential? It will be decaying exponential, right? So this will be -1/20 e raised to power -3t only. Okay, but in these cases, right, these cases my poles are on the right half plane, right? Poles are on the right half plane. Okay, I hope you remember what type of exponential we used to get. Unbounded exponential, like this one, right? Why? Because what was the form for this? It was e raised to power -as, right? -80, sorry, -80. S plus a, it was -80. And you do here, what is this? It is e raised to power minus into -1 into t. It becomes e raised to power t, and it goes to unbounded. So that's why we say poles on the right half plane of the j omega axis will always give you unbounded response. We see that we are getting unbounded response. So in these two cases only. Okay, and even if one value is unbounded, then the overall value will be also unbounded because it is simply getting added, right? So this is 1/5. This is 1/4 into e raised to power t plus 1/4 into e raised to power t plus 1/5 into e raised to power 2t. E raised to power 2t, right? So yeah, what we are seeing, for a bounded input we are getting a unbounded output. Unbounded output. Okay, so yeah, this is the main point that I wanted to get in your head, right? So like you used to say, pole on the right half plane is always gives us unbounded. How does it give? That's why I prove it to you with examples. Okay, so yeah, That's why now what we want to do is we want to control this, right? Control this unbounded behavior and make the poles on the left hand side. How we will do that? By changing the eigenvalues. Okay, by changing the eigenvalues. And how I will change the eigenvalues? With the help of controllability. So that is what basically this key point defines. Controllability defines that all state variables are input dependent. Okay, so if a system is controllable, right? So as I explained here, that I provided an input over here, and if I see like I can control the output. Okay, I can control the output with my output of the state variable, then I can say that the system is controllable. Okay, and if it is controllable, I can move the poles and make it stable, right? So that is like, we will also do a few more examples, and from there we will understand, right? So don't worry. So controllability defines all state variables are input dependent. That means all the state variables can be controlled by my controlled input. Okay, we'll understand. Now controllability is the ability of input to affect the state variable of the system. As seen from the first example, we affected the like state variable of the system with the help of input, right? With that RC circuit and initial voltage. Also controllability is the ability of the input to affect the eigenvalues of the system. Basically we are controlling the state variables, right? If the state variables are controllable, then the system matrix A is controllable, then the eigenvalues can also be controlled. That's why this point. Now what is the next point? A system is said to be controllable or state controllable if it is possible to transform existing state of the system to any desired state by applying the input in finite time. What does this mean? So in the first example, right, I had a RC circuit and like initial value and one input, right? So I can get to any desired state, that this VC, with varying my input, right? If I vary my input to some certain value, I will get my desired VC. Basically that is what this is saying, that we can get to our desired state at any point of time. We just have to give the appropriate proper input and we'll get our desired output. So yeah, that was the main thing. Okay, in this now, right, I will show you how we control, and what do you mean by control, like controllability, the basic theory you have known. Now how I'll show you how we control. So what we do is, we know the state equation. Okay, this is just bread and butter for us. So what is this called now? Like my actual input will be something else. Okay, but this is known as the control input. Okay, that's why like there are two inputs, R of t and U of t. So you get confused, but both are inputs, that's fine, but we'll go along. Now we will understand why and how. Okay, so this is known as controlled input. Okay, this is known as controlled input, and this is the, what is this? The change in the state variable. So I have to control the change in the state variable so I can get to my desired future value. Okay, get to my desired future value. This is the change in the state variable. So that like I have to control this. I can get to my desired state, future state, basically desired future state. Okay, so yeah, that is the main thing. That's why now here, right, I only want to get my change of state variable in terms of the input itself, not with the initial conditions. As this x, right, x, if it has some initial conditions, then I will have to take care of that also. So what we will do, we will assume that initial conditions is 0. Like one thing we know, that what is my x of s, like in Laplace domain, what is it? It is basically the state transition matrix times x of 0 plus my state transition matrix times b into u of s, right? I hope you're revising the formulas. So this is all this you have to revise the formulas. Also obviously understand that this is the, what is this? This is a 0 input response and this is the 0 state response, but for the state, right? This is just for the state, this is not the output. So for output, simply what you have to do is multiply C with this, then you can call this one 0 input response, and this is 0 state response. Okay, so yeah, but I only want the 0 state response. Okay, I want to find the state, I have to find the values of future values of state for 0 state response, that is due to the input only. So what I will do, assume initial, like initial conditions to be 0, okay, assume initial conditions to be 0. So my initial condition is 0, this x of s, right, this x of s will get changed to simply phi of s times b into u of s. Okay, so this is what my x of s will get changed to. Okay, so but I want the time response, right? So I have to, what I have to do, I have to take the Laplace inverse. So this is x of t equals to Laplace inverse of this. We have already done this multiple times. Laplace inverse of this whole thing, phi of s times b u of s. Now, like that's why, right, I want my controlled get a controlled state variable, any like desired state, any desired future state, with the help of this controlled input. Okay, so I have to give a controlled input here for getting the desired state. So with the help of controllability, obviously I can get to a desired state, but that also means I can make my system stable also from unstable. Okay, so that is also one help for the controllability. Now, right, what we'll do, we'll do the block diagram representation of state space equation that we haven't done yet. So these are my state space equations basically. Okay, so I should write here also that controllability helps system stable. Okay, that is what controllability helps, right? So basically now we'll do the block diagram representation. So this is my state variable state space representation, right? So what I will put few blocks, and from there we'll understand further, okay, how we make a system controllable, or how we make the system stable, right? So if a system is controllable, then how we make it stable, we'll show the practical aspect. So this is the equation. So can I write this in block diagram? So one thing I know in block diagram, right, this is the differentiation, and this is like just integration of this one ax. So I will have at least one integrator, that I know, right? So first what I'll do, I'll draw integrator block. Okay, draw integrator block. And so next up is what? Next up, right, I know that what is this point? This point, right, this point is x only, and this point will be my x dot, because if this is x, then like the integration of x dot will be x only. Okay, so this is one thing. And like what do I do next? So I know, right, this is x dot and this is x. Now x, right, x is getting multiplied with a, and we are adding with b times u, and that is giving us the x dot. So what I will take a feedback from x here, and I will take a block of gain a, I will multiply with a, and I will add it here, because input is generally on the left hand side. Okay, we have u over here, and I have another gain block of b. Okay, and this is getting added, this is getting added, and this is getting added. Okay, so yeah, both of them are getting added, right? So again, right, this at the output, we know my output will be simply c times x, this c times x, right? So my output will be simply c times x. Okay, this is y and this is u. Okay, so yeah, from here I can like derive the block diagram, basically just derive the block diagram in front of you. Okay, so now right now I want to control it. So if my system is controllable, if for say I know my system is controllable, this system is controllable, now I want to control it. How will I control? I will control it by adding a state feedback. Okay, that is the practical way how control engineers control our system. So I will write this in previous page actually. State feedback, right? Now if I use a state feedback, what I will do? So adding state feedback, right? If I add a state feedback, right, so I will again copy this and I will take some feedback with the state and I will take a reference input, I will subtract those two, then I will pass it on to the next state. So yeah, let me draw this, then you will understand. So this is right, so let me draw this more formally. This is x, this becomes x dot. Okay, so now right, what I will do, I will take a feedback from the state variable itself. So this is x, right, and this is x dot. So yeah, now again this is, I will take a state feedback of gain k and I will give it as negative feedback. Okay, negative feedback, and what I will do, I will add it to my this input. Okay, and I will give some reference input. So this will become my control input. I will explain it to you. So I will add, like, subtract it to the reference input. Sorry, I will subtract it to the reference input. So this will be my reference input actually. Okay, this will be my reference input. Okay, I will subtract, I will give it negative feedback. Why? I will show with examples also, but generally, right, negative feedback systems can only make a system stable, right? Okay, if it is going on unbounded, it can make it bounded. Okay, if it is going unbounded in the negative direction, it can make it again bounded. But positive feedback, we only keep on making it even more unbounded. Okay, so yeah, we will understand that also, but for now this one. So I have done the basic chapter, right, and taught you the concept of negative feedback and positive feedback. So yeah, what we will do, I will take a reference input, right? So this is just a thing that we do. This is not like a concept or anything, this is the actual thing that we do, practical thing. So we'll take a reference input and give it this here. Okay, r of t, and this u, right, this u now becomes my controlled input. Control input, right? So this u becomes my control input. Now what I am doing, I am changing this input with respect to some reference input and measuring the state variables. So what we are doing here is measuring all the state variables. So that's how a system becomes controllable, if you are able to measure all the state variables. That is very important. That also will come to in next lecture. So here, right, what we are doing is we are measuring all the state variables. Okay, we're measuring all the state variables basically. So by measuring, then I'm giving to feedback with respect to the reference input, I'm getting my control output, and that will help me change the future state, right? That will help me change the future state. Okay, so let me write this in equation format, then you will understand. So here, state equations with state feedback. So my new input, right, control input, what does it become? U of t becomes r of t minus some gain k into x, right, the present state. Okay, now what is my future state basically, or what is my change in state with respect to time? So my change in state, right, x dot of t equals to ax plus b into r of t minus kx. Okay, so this is basically my change in state. So x dot equals to simply a minus bx. I'm just manipulating the equations. Okay, so not bx, this becomes bk, right? So this becomes b minus bkx. So this becomes b and x is in the common. Okay, as it is in the post multiplication, I can take it common, right? So and this becomes again b r of t. So this is my like new input, and my system matrix, right? System matrix is changed, so I can change the eigenvalues. So system matrix is changed with respect to this, right? bk factor. So system matrix is changed hence what I can do is change eigenvalues. Or poles, or you can say I can stabilize the system. Okay, so yeah, this is what the main point. Okay, so here are a few key points. Just like see all this. So here, right, what is the key point? All the state variables should be available to the state feedback of the key block. Okay, that is one important part. As I'm doing this, right, like this is just for a single element. Let's say it's for multiple elements, then all of the state variables, right, this state variable should be available to my input block. Okay, for measurement, should be available for input block for measurement, right? Else I won't be able to take the feedback of that particular state variable, and that won't be able to control that particular state variable. I won't be able to get to my desired future state for that particular state variable, right? So yeah, that is important. Then what I will call my system as uncontrollable. Okay, we'll also do one example, and from there we'll understand. So that is the point, this one. So what does the second point tell us? Second point tells us is we won't be able to control that particular state variable if it isn't available to the state feedback. So this equation, right, this equation won't be available, like this change in I won't be able to control the change of the state with respect to that input, right? B into k won't come in that particular row. Okay, and if it doesn't come, then I won't be able to control the change in the state, and I won't be able to get to my desired state at the output, right? So basically we have to measure all the state variables for the system to be for us to get to a desired state, and then only the system will be called as controllable. We'll take one example later and we'll understand. Okay, but for now you may have questions that why is this negative feedback, right? Why we are giving negative feedback, okay, and not positive feedback. Okay, so I will take one example. Even though in negative feedback also, in the first chapter itself I've explained to you that negative feedback helps us like in stabilizing the system, and positive feedback doesn't. Okay, but still here, right, here I will take one example to show you that I will use like both positive and negative feedback, and I will see which feedback stabilizes the system and which doesn't. Okay, so what is the question? Question is stabilize the following state space representations using positive and negative feedback. So you have to stabilize the following this state space representation. This is just a first order circuit. Okay, that's why we have only 1 cross 1 matrix. Okay, so to stabilize the following state space representation using both positive and negative feedback, and also we have to shift the poles to -1. Basically, if pole is in left half of the S plane, then it will be a stable system, right? It will be a stable system. So that's why basically this is the state space representation. So first what I will do, I will choose first negative feedback, and I will see if I can make the system stable or not. Then I will choose positive feedback. Okay, so where does the pole lie currently? Okay, let me draw the sigma plus j omega plane. Okay, this is sigma and this is j omega plane, and this is my +1 and this is my like -1. I have to shift it here, right? This is my current position of pole. So poles are like this only. Okay, so I have to shift this here in this region, right? To shift this in this region. So currently what is my eigenvalue? Eigenvalue currently is my 1, right? It is equals to the pole itself. Pole is 1. Like here, right, I can see that this eigenvalue of this is 1, right? Eigenvalue of this is 1. Why? Because this is 1 cross 1 matrix, right? 1 cross 1 matrix, the eigenvalue itself will be the matrix itself. So currently it will be 1 only. Even if you want to prove it, you can prove it, right? So like let's see, like if you want to see the poles, right? If you want to see the poles, so let's do this thing, the equation. Okay, let me copy the equation basically. So what is my a is 1, right? And what is my b is again 1, and what is my c is also 1. Okay, everything is 1. Okay, so like what is my transfer function? My transfer function is basically si minus a inverse c times b, right? So it is 1 only, and it is s minus 1, okay, inverse times 1. So it becomes simply 1 by s minus 1. So from here also I can understand that my pole will lie in the +1, okay? Or from this equation, okay, from here directly I could understand the eigenvalue is 1, so pole will lie at this +1, okay? So yeah, that was basically about the current situation. But what do I want in next situation, right? So I want to move my poles to lambda dash, which is -1. So I want to move my pole to -1. So I have to change my eigenvalues of this matrix, right? How will I change it? By using a state feedback. So I will basically copy this feedback system, okay, and from here we will understand, okay? So let me copy this state feedback system, right? This is x dot, okay, this is x dot. So now, right now, so we first of all we are using negative feedback. So this is k block, so we have to find the value of k for which this becomes the eigenvalue moves to -1, okay? Or can we even move this eigenvalue to the negative direction? We have to check that first, okay? So what I will do, again I will write the equations, right? So what will be my u will be x times k, and this is minus, so minus k x plus r t, right? So this is plus, this is minus. So what is my u of t? It is r of t minus k times x. So simply what I will do, again, like I will replace this equation in this place. Instead of u of t, I will replace this, right? So my x dot of t will become simply x of t plus this r of t minus k times x, right? So okay, I will not write the time because we know it is a function of time. I will just ignore the time for now, okay? And this x dot of k is x into 1 minus k plus r of t, okay, plus r of t. So now, right, this element is the eigenvalue itself, right? This element is the eigenvalue itself. So what I will do, I will simply write that 1 minus k has to be my eigenvalue equals to lambda dash, right? Okay, or you can simply find the transfer function from there also, you can do, no issues, okay? I'm doing it like this, you can calculate it like the transfer function. So this has to be my lambda dash, right? And lambda dash is -1, so I'll put lambda dash here. This is equals to -1 minus k. So what does my k become? K has to be 2, okay? Positive number, gain block 2, right? So my k has to be 2. So for system to be stable, and what do you say, and for pole to lie at s equals to -1, okay? For pole to lie at s equals to -1. So this has to be satisfied, right? This has to be satisfied, k has to be equal to. Now let's do it for positive feedback. So it may so happen, like few people might say like this, okay, don't get me wrong, people say it like this, plus here and minus k here. That is also correct, okay? That is also correct. So if you write it like that, then also it's fine, but overall we are getting a minus sign here, right? So yeah, that is one more thing you should not get confused is, generally the thing that you should keep in mind is, with only negative feedback we can stabilize the system, but if people write here plus here and minus k here, that is the same thing they are saying, right? Same thing they are saying, just in a different manner. So just take care of that. So now, right, if I apply positive feedback, I'll just check if I apply positive feedback, am I able to get a like value of k or not, right? Like proper value of k or not. So what is the proper value of k? Gain block should be positive. If it is negative, yeah, it's just a minus sign ahead of it. That is just a difference, right? So even if you choose positive feedback, right? If you choose positive feedback here, what you will get is the value of k to be negative. That means it's negative feedback only, right? Value of k will be negative. Here we got value of k to be positive. Okay, that will be just a difference, nothing else. Okay, so even if you choose positive feedback, that doesn't matter. In the final result, you will get k as minus 2. Okay, that is what we will get. So now, right, so this is k, and okay, again I will write the equation this time. So what will be my u of t? Again my u of t will be r of t plus k times x, right? So again, right, I will replace that equation. Okay, my x dot was equals to x plus u, and u is r of t plus kx. So this time 1 plus k times x will be equals to r of t and will be equals to x dot. So this value has to be minus 1, right? Because I want my pole to lie in the left of the S plane at location minus 1. So what will be this? This will be 1 plus k equals to minus 1, and what will be k equals to minus 2. So as I told you, right, we got k minus 2. What does this mean? Basically negative feedback. Okay, don't get confused. Even like whatever you have to find the final result, right? Gate is about find the answer. Okay, like concept is very important. Okay, but finding the correct answer is also very important. But without correct concept, you won't be able to find the correct answer also. So even if there is positive, right, you will get k as negative. That not an issue. So even if the question comes as positive, don't argue. Okay, the value of k will come negative. So yeah, that's what I try to like explain it to you. Positive feedback, negative feedback doesn't matter. The value of k matters. Okay, so k we get here as positive. Okay, like in this here as positive and here as negative. What does this negative signify? Basically we're subtracting, right? That means this is negative feedback only, right? That's what this signifies. Okay, so yeah, that is one thing you have to note, right? So negative feedback signifies like this minus k equals to minus 2 signifies we're subtracting. That means only we're doing negative feedback, right? That is what we're doing. So yeah, I think like that is it for this question, question, and that is it for this lecture. And in the next lecture we'll study the Kalman's test for controllability. That is the main formula that we'll use in the gate exam. Also few other concepts. Okay, so how to find the controllability of a state space representation or a state space graph, right? All those things how to do we'll understand. Okay, so that is what we'll do in next lecture. And in this lecture, what we did, I will just give you a brief overview, right? So in this lecture, right, first I explained it to you like what is controllability, like what do you mean by controllability basically. So controllability is the ability to get a desired future state, okay, with the help of a desired input, right? Control input. I will give a control input and I will get my desired state. So that is what like controllability in practicality sense means. I can control the state variables with the help of my inputs, right? If the system is not controllable, I won't be able to control the state variables with input. Okay, so I won't be able to control. So let's say like you are using laptop, right, and you're typing, but it isn't showing there. So you aren't able to control your laptop, right, and you aren't able to write. Okay, that is the main thing. So in a power plant, there are many state variables, right? There are many state variables, but with the help of the input you aren't able to control that. So that is what the controllability means. And in practical life also, like what happens, we want to control the state variables also to get to our desired state, right? Some desired state. So that's why the control engineers take the feedback, okay, take the state feedback and also feed it to the input with the help of a reference input, as I showed, right? As I showed here. Okay, so firstly I showed like what is the difference if I apply input and if the input is 0. Okay, then our state value, future state, right, changes. If there is input, future state will be different. If there isn't an input, future state will be different. Okay, so now like also I told you that future state will depend on the eigenvalues. Why? Because basically poles, right? Poles, and here we see it depends on tau. Tau is like inverse of negative inverse of poles. Okay, magnitude of negative inverse of poles. So yeah, that is one thing. Okay, so That is one thing. And now we found few transfer function examples we did. Then I told you like if eigenvalues are positive, then what happens if in the transfer function? Why we want to use controllability? If my state variables the eigenvalues are positive, then what will happen? My system will become unstable, as I proved here. So I want to make it stable, right? I want to make the system stable. So if I give a bounded input, I will get a bounded output, right? I will get a bounded output. So yeah, that is the main thing, right? That is the main thing. So yeah, that we proved few things, and here I told you like my state variable, like my state, right? State variable depends on the input, also on the initial value of the state also. So I want to control only with the input. Obviously I have no no control over this one, right? Initial value of the state. So I assume that initial value to be 0. So my state, this state variable is dependent on this input also. Okay, input also. So I will control the state variable with the help of this input. But if this particular state variable, like there are multiple rows, right? And if the second, let's say second state variable isn't connected with the input, isn't controllable with the input, then I won't be able to control that particular second state variable. Let's say there is inductor, capacitor. Okay, now I can control the inductor state, but I'm not able to control the capacitor state, right? Capacitor state values. So then what I will say, the system is uncontrollable, right? Okay, so that's the main thing. Okay, then I told you like the block diagram representation of the system, right? This is my block diagram representation of state space equation. Okay, you have to, like, this may come in gate or something, you have to be just familiarized with it, right? Be familiar with it. And sorry, assuming like now we take the feedback, right? We take the feedback and we take a gain block and we measure the state variables. From there we give a reference input, and giving the reference input we get our desired eigenvalues. And if I get my desired eigenvalues, I will get my desired poles, right? Location of poles, whatever I want. Or I in time domain, what I can say, I will get my desired time response or future state, right? That is the main aim. That is what I'm trying to do. Then I took an example and then I proved, right? With positive, negative, doesn't matter. Like even if there is positive here, this will become negative value. Okay, whatever gate exam gives you, you don't fear or something. Okay, if this is positive, this just find the value of k and k will come negative. No worries. Okay, no worries. That is the main thing. So this is the end of the lecture. Thank you for watching.